All right, so I'm going to be going over the common ion effect and a couple of practice questions for, examples. So first of all, what is the common ion effect? So a definition of the common ion effect could be the decrease in solubility caused by the addition of a common ion. So this is the common ion effect. So let's say we had like AgBr, and I'll write out the equilibrium expression for this. So this is going to be our dissociation. So we have solid AgBr here, and then these are both going to be aqueous. So if we were to add these to water, right, it would just be like finding the KSP. So I'll get into this in a second, but it'd just be like finding the KSP. So we would have Ag plus and Br minus. So I haven't looked up the KSP of the AgBr, but since it's a 1-to-1 ratio, this would be X, this would be X, and so you do KSP equals X squared, and then you would square root both sides to find X. And that would be your concentration of, this would be the solubility of this, this, and this. Now, let's say that we had, instead of this being water, we had like NaBr. And let's say this NaBr was like 0.1 molar. So I'll get more into the calculations in a second, but essentially what you're doing here is you're adding Br to more Br. So a way to visualize that, just redraw this here quickly. Is we can use Le Chatelier's principle. So if we have AgBr here, we have Ag plus Br minus. Since there's already Br here, that means that the equilibrium is going to shift over to the left because we are increasing the concentration of one of these, which is going to cause these two to go down and this to go up. And you can express that in a one of these graphs as well to visualize it a bit better. So AgBr. So we're increasing this, and then it goes down. Increase, go down. This one just goes down, and then this will go up. So that's what's happening when you're adding a common ion to a reaction. I don't know if this is supposed to be below this point or above it. I can't remember. I always got that wrong. Anyways, okay, so let's go over an example now. So this is question 14 from the textbook. I think it's page 262 or something. So we'll calculate the maximum mass of BaSO4 that can be dissolved in 200 mils of water. And if it's ever asking you like without forming precipitate or maximum mass or maximum anything, really what it means is it's just asking you what it is at KSP. Because remember, KSP, anything greater than KSP is going to be precipitate, and anything lower than KSP is going to have no precipitate. So KSP is like right the middle. It's like right at the middle point where PPT will start to form, but it's like equilibrium. So PPT will be constantly being formed and unformed. It'll like just start to form. So you could say like a little bit less than KSP is the maximum. But for the sake of these questions, we can just say it is KSP. So I'll just erase this. So maximum mass of KSP that can be dissolved in 200 mils of water. So first thing we always do is write out our equilibrium expression to see what our coefficients are. And BaSO4 2 minus. And then here we have our KSP expression. So we can see that it's a 1-to-1 ratio. So we're just going to have these, it's just 1-to-1. So looking in the data booklet, the KSP value of barium sulfate is going to be 1.1 times 10 to the negative 10th. And now, since this is 1-to-1, we can say this is x, so it's x squared. And then if we square root it, putting it into Desmos, you should get 1.05, depending on how many decimal like sig figs you want to use. I think we would just use 2. So it'd just be 1.0 times 10 to the negative 5th. Equals x. And now this wants us to find the maximum mass. So this is in molarity right now. So if we want to find mass, we should probably go into moles. So using the NCV triangle, NCV, if we want to get to moles, or N, that means we need to multiply concentration by volume. So we have the concentration here, and we have a volume right here. So we'll use 1.0 times 10 to the negative 5 times our 0.2 liters, and just plugging that into Desmos, times 10 to the negative, what was it, 5? Negative 5th times 0.2, we will get 2, is that right? Yeah, I think that's right. 2 times 10 to the negative 6th. Moles. And now we'll do moles to grams. So the molar mass of BaSO4 should be, let me check my periodic table. I should have wrote this down beforehand. So barium is 137.3 plus the sulfur is 32.1 plus 4 oxygen. It's going to give us 233.4. So 233.4 grams, and that will give us 2 times 10 to the negative 6th times that we'll say 4.7 times 10 to the negative 4th, 4.7. So 4.7 times 10 to the negative 4th grams. So that is roughly how many grams, or the maximum mass of BaSO4 that can be dissolved. If you use more sig figs, you'll get more precise answers, of course, but this is close enough. It's around it's around 4 times 10 to the negative 4th. So that's how you do this first question. But now this second example here is asking us to find the maximum mass of BaSO4 that can be dissolved in 200 mils of 0.1 molarity Na2SO4. So I like to use an ICE table for this. So I'll quickly make an ICE table up. So Ba2 plus SO4 2 minus ICE. So, of course, BaSO4 isn't going to matter here because it's a solid, and it's not in equilibrium expressions. But we do have these. So starting out, we have a solution of Na2SO4, and it has 0.10 molarity. So Na2SO4 is in a 1 to 2, I can't fit this on the screen, but it's in a 1 to 2 to 1 ratio. So that tells us that it's also going to be 0.1 when these ions dissolve in their solution, right? Because we already have a solution of Na2SO4. That means we're going to have 0.1 molarity, or the concentration of sulfate is going to be 0.1 moles. So if we're adding Ba2, that means initially we have 0.10 molarity. We have no Ba2 initially. We add Ba2. Remember, this is all 1 to 1, so we're adding X. We're also adding X to this one. That means at the end we'll have X here, and we'll have 0.10 molarity plus X. So now to find the KSP, or well, we already have KSP. We remember that it is the what was it? It was like 1.1 times 10 to the negative, 1.1 times 10 to the negative 10. So 1.1, 10, negative 10 is going to equal, and remember the KSP expression is written like this. KSP equals Ba2 plus SO4 minus 2 minus. So SO4 2 minus, that means this is going to be X, and this is going to be 0.10 plus X. So one of the confusing parts, or I think is a confusing part about this, is why we can disregard the X within the brackets here. So remember that KSP is the product of the concentration of these two ions here. So that means if the number of these two multiplied together is going to equal this, and KSP is this small already, that means X, the concentration of this and the concentration of this, must be even smaller, right? So 0.1 is 1 times 10 to the negative 1, I think, or 2. I'm bad at decimals. I think it's 1, yeah. So this one is to the negative 10th. So that means adding X to 0.1 would be like, we would get like something like this, probably. That is extremely negligible. It's still 0.1. That is why we can disregard the X in the brackets. We not the one on the outside, but the one on the inside is disregardable. So that means 1.1 times 10 to the negative 10th is going to equal 0.10x, and then if you divide everything by 0.10, then you'll get x equals 1.1 times 10 to the negative 9th. So that is the maximum That's not the maximum mass, that's the solubility. So, and then from here we would just do the same thing that we did at the last question. So you take this, you would multiply it by, so I'm just going to free up some space here. So we would do 1.1 times 10 to the negative 9th times 0.2. That would give us our moles. So so that gives us 2.2 times 10 to the negative 10th. And then we just multiply this by the 233.4 that we got last time. And that will give us 5.1 times 10 to the negative 8. 5.1 times 10. And that's in grams. So that's how many grams, that's the maximum mass of BaSO4 in grams that can be dissolved if there is that extra ion present. And notice how, oh no, never mind, it's not here. Okay, it's because I erased the other one. I'll show it next though. So getting into this a little bit further in terms of solubility. So with this one we're trying to estimate the solubility of silver chloride in 1 times 10 to the negative 4th molarity NaCl at 25 degrees Celsius. 25 degrees Celsius is just because it's that's like the equilibrium thing, solubility, whatever. So I've written out here just the equation, the KSP, and the KSP value of AgCl from the data booklet, just because it's just to make it go quicker. So what we do here first is, and I just want to make this like, so this is kind of like a broad rule that we can apply. So due to the presence of a common ion, we should expect that the solubility of AgCl in NaCl, right, because the Cl is common, to be lower than in pure water. So this is like back here, remember? So we're essentially going into this a little bit more quantitatively. So if we have just in pure water, we have our KSP, and this is in a 1-to-1 ratio. So that means if this is X, this is X, this is X dissolves, whatever, I don't feel like writing all that out. This means that this is X squared. So if it's just in water, we can square root both sides. 1.8 times 10 to the negative 10th, square root that, 1.3 times 10 to the negative 5. So that's the solubility of silver chloride in water. So there's no common ions. Now let's see if this prediction is correct. So I'll set up the ice table again, because I really do think that that is the easiest way to visualize and to, figure out where the extra concentration of the ion really like fits in the whole idea here. So I, C, E. So we have no AgCl to start with, but we have Cl ions from the sodium chloride, and we have 1.0 times 10 to the negative 4th molarity of chloride ions. So this one will increase by X, this one will increase by X, so at the end we'll get X, and then 1.0 times 10 to the negative 4th plus X. So that means our KSP, 1.8 times 10 to the negative 10th, is going to be equal to X times 1.0 times 10 to the negative 4th plus x. Remember from before, we can disregard this x, so we'll just have 1.0 times 10 to the negative fourth x, excuse me, and then 1.8 times 10 to the negative 10th. We can divide everything by 1.0 times 10 to the negative fourth, and we will get that x is equal to, let's just see here. Nope. Divided by 1.0 times 10 to the negative fourth. So we'll get 1.8 times 10 to the negative sixth. Molarity. So, is our prediction true? Well, this one's to the power of negative sixth. This one's to the power of negative 5. So this one is a lot bigger. So this shows that it's true. If we're dissolving it in a solution with a common ion, that means that it will have a lower solubility than if it was dissolved in a solution without a common ion. And again, going back to the sort of more qualitative, like less numbers understanding of it, it's because we're increasing the concentration of this ion, which is causing a left shift over. And the left shift is going towards the solid side, and the solid side is not the soluble side, right? It's decreasing the solubility. It's forming a precipitate instead, which is like not solubility, right? So I got one last example, because this one I got from like organic chemistry tutor. This one involves, like, it's not all one-to-one, so I think that's important because that would probably be on a test or something. So first, what is the solubility of PbF2 in a saturated solution of lead 2 fluoride? So this is just asking, what's the solubility of PbF2 when it is fully saturated? No common ions. So the KSP that's given in the video, and remember the KSP expression, we'll just write this out so we can reference back to it. Pb2+, but in this case we have F minus squared, right? Because PbF2 goes into Pb2 plus 2F minus. So the KSP shown is 4 times 10 to the negative 8th. And so here we have x, but this is 2x. So that means we'll have x times 2x squared. So this is just like a standard KSP thing. So if we apply the exponent, that will get us a 4x squared times the x will give us 4x cubed equals the 4 times 10 to the negative 8. And then what we can do is just put the whole thing like this and divide it by 4 on each side. So putting that into this calculator will be 4 times 10 to the negative 8, right, over 4 will give us 0.002, okay, we'll just say 2.2 times 10 to the negative third. Right. 1, 2, 3. Yep. All right. So this is it this is the solubility, or the molar solubility in a saturated solution. But now it's asking us to calculate the solubility of PbF2 in a 0.5 molarity sodium fluoride solution. So again, I really recommend that you make an ice table for this. So we'll do PbF2, Pb2 plus 2F minus ICE. So we have none of this to start with, but we do have 0.5 molarity of F2 from this solution here. And you're not multiplying by 2 yet because this 0.5 is coming from this, which has a 1-to-1. If this was something like, I don't know, like MgF2, right? Then that would go into 2F minus, and then Mg2 plus. So that means that this would be a 1-to-1 to 2. So this would actually be like 1 molarity F minus. So you have to pay attention to where the source is. So this will increase by x, but remember this one will increase by 2x because of the coefficient here. So in the end we have x, and then we have 0.5 plus 2x. So we'll take the KSP, 4 times 10 to the negative 8th of the PbF2. And it's going to be this. This is the KSP expression, right? Remember that this is squared. I don't know why that looks weird. Squared. So this will be x, and then for the PB, and this one will be 0.5 plus 2x squared. Now, despite it still being doubled, we can still disregard the x in the brackets, but that doesn't mean that the coefficient goes away or anything like that. So that means that our expression will now be 4.10 to the negative 8 equals x times 0.5 squared. So 0.5 squared should just be, I don't know, I'm bad at math and I'm lazy, 0.25. So this will be 4 times 10 to the negative 8 equals 0.25x. Then we can just divide the whole thing by 0.25, and I'll just write it up here. That gives us x equals divided by 0.25. So that gives us 1.6 times 10 to the negative 7th. So that's the solubility of PbF2 if it's in a solution like this. And I erased it now, but looking back, this right here, nope, that's not it. This was the solubility for when it was just in water, or just there was no common ions, right? We had the 2.2 times 10 to the negative 3. So I'll just write that right here, 2.2 times 10 to the negative 3. So again, we can look at our prediction here. The presence of a common ion, we should expect the solubility of this in the solution with the common ion to be lower than a solution without the common ion. And that is still true here, because something raised to the power of negative 3 is going to be a lot bigger than something raised to the power of negative 7. So just to recap, we can understand it a lot better, in my opinion, with ice tables, because that shows us what we start with from these solutions. And then we can disregard the x in the brackets because of how small the number is that would be added. We can predict that the solubility will be lower when there's a common ion than if there wasn't. And the presence of a common ion will decrease the solubility of a given solid because of Le Chatelier's principle, increasing the concentration of one ion, which causes it to shift over to precipitate, which means that it's less soluble. So